All right, our next speaker is Shai Golan, who will tell us about an improved algorithm for k-Dyck edit distance problem.
Okay, thank you, Ad. So this is a joint work with Dvir Fried, Tomasz Kociumaka, Tzvi Kopelowicz, Eli Porat, and Tatiana Starkowskaya. What is the Dyck language? So Dyck sequence is a sequence of balanced parentheses of different types, and in the Dyck language we have all the Dyck sequences. So the Dyck edit distance problem is the problem where we are given an input sequence S, and we consider three edit operations: insertions, deletions, and substitution. And we want to compute the smallest number of operations that one should perform to transform the sequence S to a valid Dyck sequence. So, for example, if we consider this sequence S1, then as you can see, it's not balanced. And we can fix it in one edit operation, in this case substitution of the second symbol, and therefore the Dyck edit distance of this sequence is 1. In the next example, we have a sequence that we cannot fix with one edit operations, but we can do it with two operations, and therefore, for example, if we delete the first parenthesis and insert a new closing curly bracket, then we fix the sequence. Therefore, the Dyck edit distance of this sequence is 2. Actually, one can consider only deletions and substitution in this specific language of the Dyck language. And the reason for this is that the only reason for someone to insert a new parenthesis to a given sequence is to match other parentheses that wasn't matched originally. But instead of inserting a new symbol, a new parenthesis, we can delete the original parenthesis that was without any matching parentheses. So for example, here we can do with the same cost of two operations, we can fix the sequence. So even if we don't consider insertions, the Dyck edit distance is still 2. And for this problem, we have a conditional low bound by Abud Bakos and Vasiliska Williams that claim that no one can introduce an algorithm which take less than n cubic time for combinatorial algorithm. It's based on the hardness of k-Dyck. So since the problem is hard, we consider a restricted version, which is the k-Dyck edit distance, where instead of computing the exact edit distance, if the Dyck edit distance is more than k, we don't care about its actual value, but just the fact that it is more than k, and if it is small Dyck edit distance less than k, then we want to know the Dyck edit distance exactly. So the results for this problem in the combinatorial algorithms regime, of course, there is the classical dynamic programming algorithm that we will see that matches the lower bound and takes n cubed time. On pod 16, Bakos and Onek introduced an improved algorithm for small k, which takes time n plus k to 16. And in this paper, we introduce an improved algorithm that takes n plus k to the 5. If you allow fast matrix multiplication, so we are in algebraic algorithms, then Bridgman et al. Show that one can reduce the exponent from 3 to slightly less to 2.86 or 2.82. Depends if you allow randomization or require just deterministic algorithms. Actually, in this SODA, the talk was yesterday, the running time for the randomized algorithm was slightly improved by G et al. And similarly, we show that our result of n plus k to the 5 combinatorial algorithm can be slightly improved using similar techniques. So the exponent is slightly less than 5. Again, it depends whether we require the deterministic algorithm or allow randomization. So let's start with the classic dynamic programming algorithm. It's in level of undergrad students. So the idea is pretty standard. We consider every substring of the input between position I and j, and we consider we have a recursive function that consider all the options to partition this substring. So all the options are just split it into prefix and suffix with any way that it's possible at any position, and compute or use the already computed in the dynamic programming table Dirac-Eddy distance of the prefix and the suffix, and take the sum of them and take minimum from all these values. And the only other option is to match the first and last symbol and take the Dirac-Eddy distance of the inner part. The cost of matching the first and last symbol may be 0 if they are actually matched, or 1 as in this example. And there are also cases where the cost of matching the first and last symbol will be 2 if the first symbol is the closing parenthesis and the last symbol is opening parenthesis. So the dynamic programming algorithm just consider all the options and take the minimum from all of them. The computation time for every substring is order of n, and there are order of n squared cells. Therefore, the total time is n cubed. Now I will show how we improve our first step in the paper is to improve the running time of this algorithm from n cubed to n squared k. And we do it in 3 steps. The first step is just giving some definitions of heights, peaks, and most important values. Then we show how to reduce the number of values to order of k. And then we show how to reduce the computation time of every cell for every substring to be, instead of order of n, it will be order of the number of values. And due to the previous step, it will be order of k, and therefore the total time of the algorithm will be n squared times k. So the definition of heights and values was already appeared in the paper of Bacchus and Onak. So the idea is that for every position in the string, in the input, we define the height of position I as the difference between the number of opening parentheses and closing parentheses in the prefix of the sequence up to position I. And if we write the string, the input above this height graph, then you can see that every uphill slope is composed of only opening parentheses, and every downhill slope is composed of only closing parentheses. And then the definition of peaks and valleys are pretty intuitive, where peaks are positions between that are contains opening parentheses followed by closing parentheses, and values are just the opposite. So now when we know what are values, let's see how we reduce the number of values in S. So the idea is, it's already appeared in the paper of Bacchus and Onak, is to start with a greedy process. So greedily we pick every adjacent opening and closing parentheses of the same type that match themselves, and we match them and remove them from the string. So for example, we match the first pair, and then we match this square brackets pair. And then after we remove this square brackets, the parentheses, the green parentheses here are also called adjacent, and therefore we match them also. And we repeat this process again and again until there is nothing else to match. And it's pretty intuitive, but Bacchus and Onak proved it formally that the Dirac-Eddy distance due to this process doesn't change, and therefore the Dirac-Eddy distance of S prime now is exactly the same as the original Dirac-Eddy distance. But now we have the following property. When we are looking on the peaks of the resulting string S prime, we know that every peak is a position where we must fix something. It's a position where we have opening and closing parentheses of different type, and we must pay some editing, either deletion or substitution, for this peak, and therefore the Dirac-Eddy distance is lower bound by the number of peaks in S prime. And therefore, we can assume that the number of peaks is order of k, since if the number of peaks is larger than k, then we can just report that the Dirac eddy distance of the input is larger than k, and we don't really need to do anything else. And if the number of peaks is order of k, then for sure also the number of valleys is order of k, since between any two valleys there is a peak. That's it. And now we introduce a novel lemma that says that we can actually speed up the computation time in the recursive function of the dynamic programming algorithm. So if we consider some substring between I and j, instead of considering all the partitioning positions between I and j, it will be enough to consider just small amount of them, which are the partition where the prefix is of size 1 or 2. This is in this area. The partition where the length of the suffix is 1 or 2. And most important is all the positions in between, we can just focus on the valleys. And for every valley, consider one position to the left of the valley, the exact position of the valley, and one position to the right of the valley. So for every value, we will consider just 3 positions, and we ignore all the other positions between I and j. And let me give you the idea of the proof. So the idea is that assume that there is some optimal partition. It could be the case that there is an optimal partition that is not on a valley or one position to the left or right. But we will show that if there is a position, an optimal partition which is not close to a valley, then there is also another optimal partition which is slightly closer to a valley, either in p-1 in this case or in p-2. There are cases where it's p-1 and cases where it's p-2. And since we will show it, then we can repeat this argument again and again until we conclude that either in the valley or one position to the right or to the left of the valley, there is also an optimal position of partition, and therefore it will be enough to consider what we actually consider. So let's look on this partition on position P. So then, since P is in uphill slope, we know that it composed only from opening parentheses, and therefore we know that the last position in the prefix now is an opening parenthesis. However, it cannot match anything without edit because it's an opening parenthesis and it's in the last position. Therefore, we must pay something for it, and we must edit it with either deletion or substitution. If we delete it, then let's consider what happened when we partitioned the string at position p-1. Then we can do exactly the same set of operations in the prefix and in the suffix, except that now the deletion of this opening square brackets will be charged on the suffix instead of the prefix, but the total number of operations will be exactly the same. And therefore, in this case, if the partitioning in P is optimal, then also the partitioning in p-1. There are some other cases to analyze where when the last character, last symbol is substituted instead of deleted, but the idea is the same. And you can find the details in the paper. And as I said, if we apply this argument repeatedly, we conclude that looking just on partitioning on the valley or the neighbors of the valley is enough, and it will find some optimal partition. And therefore, the total computation time for every I and j, for every cell in the dynamic programming table, is now, instead of order of n, we can bound it by the number of valleys that we already said it's order of k, and therefore we reduce the total computation time to order of n squared k instead of order of n cubed. In the remaining time, I just want to give some ideas of how we further improve the running time for small k to order of n plus k to the 5. So the idea is that let's start with considering some degenerated case where we don't have values at all. And so the input is composed of a sequence of opening parentheses followed by a sequence of closing parentheses. So we observe that, let's look on the dynamic programming table. And if we have two positions, one from the uphill slope, the region of opening parenthesis, and the other is from the closing parenthesis region, where their height is pretty different, is different by more than 2k, then whatever k-edit operations that one could apply will not make them on the same height. And as we know, substring is sequence is balanced only if the height of the prefix, the height of the beginning point and end point is exactly the same. And therefore, if we have just k-edit operation in our ability, and the height difference is more than 2k, then these two positions cannot be matched whatsoever. And therefore, we can conclude that the Dyck edit distance of the substring between I and j, which is denoted here in the dynamic programming table, is for sure larger than k. And therefore, we can ignore it. And if we draw the regions in the dynamic programming that we can claim this fact, we get something like this. And as you can see, the only regions that actually interesting are what is not so dark yet. And for this, we are starting with computing just naively the Dyck edit distance of pairs of positions, where one is from the left red line and the other is from the right side of the left region. And this region is a square is the red square in the dynamic programming table. What we actually want to know, we want to know the output, which is the Dyck edit distance of the first and last position, which is in the right top corner, and we draw here the square of the 2k on 2k output that we want. And the idea is that instead of computing all the region between the red and the blue square, one could use we are using the Landau-Wishkin technique. That if you know it, then great. It's using a suffix tree with longest common extension queries. But if no, just you can think about it as a black box that enable us to extend the result that was computed in that were computed in the red square to the result of the blue square. And the important thing is that after order of n pre-process time to build this suffix tree, the computation of the blue region is of the blue square takes only order of k squared time. So this triangle, we think about it as a trapezoid. We will see in a moment why. And it's the generated trapezoid, and the total time we spent for this trapezoid is just order of k squared time after the linear preprocessing. So now, what we are doing when we have a general input. So we introduce in the paper a way to partition the input into order of k trapezoids. So for example, here we have T1, which is the generated trapezoid is before, and T2 is similar, and T3 here, as you can see, is not the generated, is really trapezoid. And what is the idea? The idea is that when we are looking on positions in the trapezoid, we don't really need to think about values. Earlier we proved that it is enough to consider just partitioning in values, but these trapezoids, all the positions in these trapezoids are pretty far in their height from values. So for example, if we consider string that starting where my mouse is hovering right now, we don't really need to consider this value. Why is it? Because the difference in the heights between the starting position and this value is more than 2k, and therefore if we consider partitioning in this value, then the cost of fixing the prefix will be more than k, and therefore we don't really need to consider it. And therefore the trapezoids are solved as we described earlier with Landau-Wishkin algorithm, and all the other positions are positions in regions which we defined as clusters, and we have the property that the total size of the cluster is order of k squared position, and therefore even if we consider all the pairs of substrings that begin in one position, one white position, and ends in one white position, it's only k to the 4 cells, and therefore we get order of k to the 5 computation time by k time per cell, and therefore in total we get n plus k to the 5, which we can improve slightly if we use the fast matrix multiplication, and that's it. Thank you. And if you have a question.
Thank you very much to the speaker. Anybody has a question? I have a question. What do we believe that the correct running time should be n plus k cubed, or what do you think?
It's really good question. The best slow one we have now for combinatorial algorithm is indeed n plus k cubed. I tend to believe that this should be the right answer, but maybe not. I'm not really too sure about it.
All right, thanks. Anybody else? All right, let's thank Shai again.
Okay.
All right, this is probably it.